Good afternoon. Welcome to EE222. Just give me a few minutes while I log into the Moodle shell. We were looking at number systems and how to and how we can look at negative numbers. Okay, so I've sent out two messages today. This is targeted at the students who are stuck in the region. For those of you who are in Fiji, it is advised that you come and attend the lecture face to face. All right. Okay. All right, let's begin with our lectures today. Last week we were looking at how to go about doing the subtracting numbers. Now, the method for subtracting numbers is that you've got to add to a negative number. There's no such thing as a direct subtraction. So when you do x minus y, what you're actually doing is x plus negative y. All right? I think that was quite straightforward. And first we made the attempt with using some direct subtraction, and we found that there are some issues, right? We tried to apply sign and magnitude for subtraction. And what we found was when we use sign and magnitude for subtraction, sometimes, like in this example of 7 minus 4, it worked properly. You know, we allocated for the overflow bit. And when we did the next problem, which was 6 minus 2, which is the same as saying 6 plus negative 2, we found that it gave the wrong answer. So sign and magnitude was not a good method. So therefore, we now move to a new method. We move to a new method called the complement method. So today is, what date is it today, guys? 5th, right? 5th April 2022. This is week 3, lecture 1. Yeah. Okay. All right. And today, what we look at is something known as the complement method. Okay? All right. Now, and why do we have to go to another method? Well, we've already discovered that using sign and magnitude doesn't work out, right? It worked out with one set of digits but didn't work out with the other set of digits. So we've got to use another better method called the complement method. Now, the word complement it means opposite, right? In this case, it means opposite, right? Opposite, okay? So opposite, you could think of it as in terms of binary. So the word complement in English means opposite, right? So opposite or something to contrast, something different, right? The word different, right? So if somebody compliments you, they are being different from the others because the others are silent and one person has complimented you on your sports or on your grades or something like that, right? Or on your footwear, whatever it is, right? But in our case, complement means opposite, and it actually means that you've got to flip, we've got to flip, or we've got to apply flipping the bit, right? Or flipping the bits. All right, let's start off with one's complement. Let's start off with something called one's complement. And actually, one's complement is not that important, right? It's more so to get to something else called the two's complement, right? Remember, if you flip back on our notes, you'll see that I've said, hey, we're going to use sign in magnitude and you're going to use the complement method, right? So the complement method is our second method. You see this number 2, right? So let's label that as number 2. All right. Now, let's start off with something known as one's complement. Now, we want to convert, so we want to convert a number to the one's complement system. So we want to convert a number to the one's complement system. Right? Just like how we had the sign in magnitude system, this is another system, the one's complement system. Now in the one's complement system, straightforward, two rules. Number 1, if it is a positive number, then we leave the number as is and we leave the number as is and we find the natural binary. All right. Number 2, if it is a negative number, we find the natural binary and then we flip. All right, let's move to example. Example 1. Let's consider, in example 1, let's consider the number positive 11. It is a positive number, so we just go ahead and convert it to natural binary. So natural binary, it will be what? 1, 0, 1, 1. All right, let's consider negative 11. Right? For negative 11, okay, maybe find, first maybe over here the step is get the absolute value and then find the natural binary and then flip. All right, so negative 11. So for negative 11, what we're going to do is we take the absolute value of negative 11, which is actually equal to 11. Now 11, we are aware, is 11 is the same as 1, 0, 1, 1. Now, so that's step 1. So maybe that was step 1, that was step 2, and then flip is step 3. So step 1, step 2, step 3. Now that we flip the bit, what do we get? That will become 0, 1, 0, 0. That's in one's complement. So we put a ones over there. Okay, we put a ones over there. Okay, right? So there, what does that say? That says that, what have we done over here? Over here we flip. Right? So this here is one's complement for negative 11. Is one's complement for negative 11. Okay. Let's try another one. Let's try another example. Example 2. Let's try negative 6, and we want it in 4 bits. All these systems, I want you to note down. I'm not going to write down everything. I prefer to only write down whatever is in, whatever we have to calculate. Whatever is theoretical, you can jot it down. And also remember, there's some notes on Moodle as well. But those notes on Moodle are not everything. You know what I was surprised with? We ran our first lab yesterday, and a lot of the students were very unfamiliar faces. I'd seen them for the first time walk into the lab. So I hadn't seen them before. So obviously it's not you guys. I can recognize some of your faces now, right? Okay. Where's the other guy? The guy who used to be over here with you guys. All right. Okay. Oh, he's here now. Okay. So, and these guys, a lot of the students, and maybe they're listening to this on Zoom, or maybe they're looking at it on video capture, or maybe you might meet them and tell them. And what I was surprised with was they had this very simple lab, not much no hardware, no software, just hand drawing, just to do something in the exercise book. And they were spending time, they were flipping through the notes on the Moodle shell. They had gone to the Moodle shell and they were looking at how to do the number conversions. So straight away I knew, hey, they don't have the exercise book, they don't have whatever the examples we've done, so they had absolutely no idea about what's going on. That was one thing I was surprised with. The other thing is, just to let you know, please make sure you look at the Moodle shell and the time of our labs. For Monday, it's from 9 till 1. You've got to be in by 10 past 9 at the latest. Preferably, you should be there by 9. Actually, the time is 9. We'll start at 9. But if you arrive at 10 past 1 or after 10 past 9, then there's going to be a problem with your attendance list, right? And on Friday, it goes from 9 till 12 and then from 12 till 3, all right? Please don't be late. Don't turn up at 1 and claim that you haven't seen that your system was saying that the lab time was different, all right? So you've got to be really in touch with the lectures in order to move forward with the course. All right, let's have a look at this example, negative 6 in 4 bits. So what I was trying to say over here is that all these negative systems, whether we're doing sign and magnitude, or whether we're doing 1's complement, or soon we'll move to something better called 2's complement, all these systems are restricted by the number of bits. That's the rule. But what we find with sign and magnitude, even when we played with the game, even we played the sign and magnitude game with the right number of bits, it still gave the wrong answer. That was the issue. That's why sign and magnitude is only good for storage. Note this down. It's only good for storage, but not good for computation. Only good as far as storage goes. So if you want to store a number and then retrieve it, fine. But if you want to apply that number and do some addition, subtraction, multiplication, it'll get messed up, right? So sign and magnitude, it is no good for any sort of arithmetic. All right, now let's have a look at this particular example here. Let's have a look at this number, negative 6. So let's follow the step. The absolute value of negative 6 is equals to positive 6, right? That's quite straightforward. You can even skip that step. You can just go ahead and, this is a lot of things which I'm doing on the book right now. It's based on, I'm teaching you, so I'm showing you little baby steps. But soon, when you do your short test and whatever, you don't need to write down absolute value of negative 6. You can just start your calculation at positive 6 straight away. All right? Okay, you don't need to show that particular step. Right? But of course, if you are coding, if you're writing code to convert a number from a negative number to 1's complement to 2's complement, you've got to go ahead and execute that line of code which does the absolute value. The computer won't do it for you. All right? Okay. All right. So positive 6 is equal to, in 4 bits, it's 110, and we add a particular 0 there. That's in natural binary. Natural binary is unsigned. Right. So negative 6 in 1's complement would equal to 1001. And we write 1's complement. All right. Now, let's go and check subtraction with 1's complement. All right, let's check subtraction with 1's complement. Let's redo that example early on. What example was it? 7 minus 4. All right. 7 minus 4 is the same as doing 7 plus negative 4. Let's do this in 4 bits. So, you have 7 and you have plus of negative 4. Now, let's over here on the sideline do negative 4. Negative 4 would equal to, okay, positive 4 would equal to 0, 1, 0, 0. Negative 4 will equal to 1, 0, 1, 1. Yeah, in 1's complement. 7 would be what, guys? 0, 111. Yeah, that's a positive number. We don't need to do anything. And then we're going to do a plus. The negative 4 is from here. 1, 0, 1, 1. Right? 1, 0, 1, 1. Let's pull a line. 7 plus negative 4 should give us a 3. Right? Correct? 7 minus 4 is 3. Let's do this. 1 plus 1 equals 0. Carry 1. 1 plus 1 plus 1. 1 plus 1 is 1, 0. Plus another 1 is 1, 1. 1, carry 1. 1 plus 1 is 1, 0. 0, carry 1. Alright. 1 plus 1 over here is 1, 0. Right. Interesting. Interesting. It gave us the wrong answer. Right. So that's in 1's comp. So we have 1, okay, this becomes what? What does this become, guy? Overflow. All right. So what is our answer? Stored answer is is 2. Okay, let's do another example. Let's do another example. So it's wrong. We know it's wrong. Let's do the same example from last time. 6 minus 2. All right, let's do 6 minus 2. 6 minus 2 again in 4 bits. And 6 minus 2 can be rewritten as 6 plus negative 2. All right. Now, let's take 2. Positive 2 would be equal to, positive 2 would be 0, 0, 1, 0. Negative 2 would be 1, 1, 0, 1. Am I correct? That's in 1's comp. Now, let's do this. 6 plus negative 2. Bang. 6 is what? Tell me 6. What is 6? Come on, guys. This should be in the... Right? And then we put a plus and we take the 1, 1, 0, 1 from here. Of course, we know the answer should be 4. And we know the answer should be what? 4 is 0, 1, 0, 0. Okay, let's do this. 0 plus 1 is 1. 1 plus 1 is 1 plus 0 is 1. 1 plus 1 is 1, 0. Right? 1 plus 1 is 1, 0. Tell me, what is the overflow? This is overflow, and this is stored. Wrong. Now, I want you to look at example 2 and example 1 and example 2. What can you tell me about our wrong answer? Yeah. Yeah, it's short by 1. It's doing the right thing, but it's short by 1. Right? It's doing the right thing, but it's short by 1. Right. So, that means all we've got to do is apply 1's complement, but add 1. Okay? To correct the answer. So, we have to take corrective measures. So, 1's complement really is not a method. 1's complement is just a system, but we are unable to apply it. So, you can write it down. We are unable to apply it because it is short by 1. If you apply, for storage we can do anything. For storage of binary numbers, you can even use an abacus if you want. Or you can use, you can use 3 monkeys or whatever you want, right? Any system which you create, you can use for storage, right? Or three bottles of beer, or whatever it is, right? But for arithmetic, we are interested in arithmetic. We don't want to just store numbers. I mean, what's the point of storing numbers electronically when you can write it down? You can write it down in your book, right? Okay? But where it comes in, where the usefulness comes in is we want to apply it. We want to use it for addition, subtraction, multiplication, division. Once you go and get all those things, then we take it further. We want to do integration, differentiation, right? Double integration, divergence, all these things. Okay, curl, all these things which you will do in ME211. All right. Now, but this is the basic. So what we note here is what we observe. Answer is wrong. But only out by 1. Only out by 1, or only short by 1. Okay, so we move to another system called the 2's complement. Two's two's complement. All right. Okay. Now we have a number, and we want to bring it to the 2's complement system. All right, number 1. If the number is positive, okay, if the number is positive, same rules apply. Like one's, sign and magnitude, all these things which you've done so far, same rules have been applied so far. Okay, if the number is positive, then we keep as is. Right? Another point. The number of bits has to be specified. Number 3, third point. And if it is positive, we directly convert to natural binary. Now, so positive has always been good. Whether we've been doing sign and magnitude, whether we've been doing 1's complement, and now with 2's complement. All right. Now, if it is negative, all right, steps. We write out the absolute value, get the absolute value, convert the absolute value to natural binary, right? Use the correct number of bits. Now flip the bits to get 1's complement. And the last one, add 1 to get 2's complement. Okay, that's a bit of notes. I probably didn't need to write it down. Maybe probably better off just by giving you an example. All right, let's take the number. Give me a number. What's your favorite number? 69? Okay. All right. Okay. Sorry, I want a smaller number. Smaller number. Right. No, let's choose number 11. Let's choose. Oh no, we've done 11 already, right? Choose another number. Let's choose 14. Let's try the question. Example 1 goes for positive 14 as well as negative 14. Positive and negative 14. So we've got to do both, positive and negative 14. And let's choose, don't choose 4 bits, let's choose 6 bits. Okay, all right. So for 14, no big deal, positive. Positive 14, no big deal. We're just going to convert it into natural binary. What do we get, guys? 14. 1110, and then it's 6 bits. So what do? Padding. Yeah, so that's, we can just say 2. Just put 2 there, which indicates natural binary, base 2. Okay, let's look at negative 14, guys. Negative 14. So in order to achieve negative 14, what we've got to do is we've got to take the absolute value of negative 14, which is equal to positive 14, which is equal to 001110 in natural binary. Now negative 18, okay, the way we do it is we take positive 18, I'll pull a line over here as such. We have to have it in the right number of bits. Right? We then take, I'll use a different color, we take 1's complement. 1's complement, what does 1's complement mean? Flip the bits. Okay, just say flip the bits. Then we add 1. One plus 1 is 10. Carry 1. 1 plus 0 is 1. 0, 0, 1, 1. Right? Is that correct? So we now have negative 18 is, sorry, oh guys, oh I should have just written 14 here, right? 14, so it doesn't change, only the question, I rewrote the question the wrong way. 14 is 1, 1, 0, 0, 1, 0, and that is in, oh sorry, 2's complement. 2's complement. Right? Okay, that's in 2's complement. Now, do you truly understand why we did this last line? Why did we do the add 1? Because when we were applying our 1's complement in arithmetic in an addition and subtraction situation, right? What were we ending it with? We were ending with a wrong answer, but the funny thing was, the answer was only short by 1. So what we done? We now make the negative number incremented by the binary bit code by 1, so that it might work in our system later on, in our arithmetic system. Let's look at another number, guys. Let's look at the number 30. And let's use 8 bits this time, negative 30. The reason why I'm not doing positive is because you guys know already. Positive is just natural binary. The only thing you got to take care of is the number of bits. Make sure you put the padding. Okay? Make sure you put the padding. Alright, now. Negative 30 is equal to, you take that absolute value. Even this step here is almost redundant. You guys are engineering students. We don't need to show you what the absolute value. You know that you can work with negative 30. Alright. Okay. Let's do 30 divided by 2 is equals to 15. Remainder? 0. Right? 15 divided by 2 is equals to 7. Remainder? 1. 7 divided by 2 is equals to 3. Remainder? 1. 3 divided by 2 is equals to 1. Remainder? 1. 1 divided by 2 is equals to 0. Remainder? 1. And we stop there. We stop there. That is our most significant bit. That is our least significant bit. As time goes along, once you start to get used to it, you don't need to necessarily write everything down. So positive 30, so over here we were looking at positive 30, conversion to natural binary. So positive 30 would equal to, what is it? 4 ones, 0, right? 410 in natural binary, but positive 30 in 8 bits, would equal to, that's 1, 2, 3, 4, 5, that means we need padding of 3 bits, followed by 1, 2, 3, 4, there we go, that's positive 30. Now, how do we go and get negative 30? Let's now attempt the problem for negative 30. So negative 30 in 2's complement. How do we do that? Well, we take our positive 30, let's pull a line over here, nice dotted line, right? We then convert that, 1, 2, 3, 1, 2, 3, 4, 0, is that 8 bits? Yes, it is, right? We take the 1's complement, there will be 1, 2, 3, 1, 2, 3, 4, 1, right? Then we add 1. One, 0, carry 1. Right? So we have 2's complement. Right? So therefore, what we can say eventually in terms of the answer is that negative 30 is equal to 1110 0010 in 2's complement. All right. Let's now apply some of these 2's complement in terms of subtraction. All right, let's do an example. I think I wasted a bit of time here by writing all this out. I think you would have been fine with me just showing you the example, right, of the steps. All right, okay. Now remember, always cater for the number of bits. All right. Let's do the example 1. Let's do bigger number. 11 minus 5, right? 11 minus 5 is the same as saying 11 plus negative 5, right? Oh, by the way, let's do this in 4-bit. Let's do this in 4 bits, right? Okay, so Now let's look at the first one. 11 in 4 bits is what, guys? It's a positive number. We have to use this one. 11 is a positive number. 11 is what, guys? 10 1011. All right. Now negative 5. Negative 5, we've got to convert it into 2's complement. Okay. Positive 5. Positive 5 in 4 bits, guys. There'll be 0, 1, 0, 1. Right? Okay. Now, we take 1's complement. 1's complement just means flip the bit. 1, 0, 1, 0. We add 1. Zero plus 1 is 1, 1, 1, 0. Okay. So that's our 5. So negative 5 is equal to 1011 in 2's complement. Okay. Now let's go ahead and do this. 11 minus 5. 11 minus 5 should comes to 6. So the way we do it is 11 plus negative 5. 11 plus negative 5. 11 was 1011 plus negative 5 is again 1011. Funny. Positive and negative number looks the same. 1 plus 1 is 1, 0. 1 plus 1 plus 1 is 1, 1. Yeah? Put a 1. 1 plus 1 is 1, 0. Right? This becomes overflow. 0, 1, 1, 0 in 4 bits is equal to 6. So answer is correct. There we go. We've done a genuine subtraction. But the funny one is, what do you see? What do you see as really, really unusual in this sum? We are doing 11 minus 5, right? And when you look at the bit pattern, both 11 and 5 have the same bit pattern, but it gave the right answer. That is what you call 2's complement. 2's complement is able to handle it, right? Because you've got positive with a different system, negative with a different system. That's why it's able to handle it. And of course, you've got to stick to the number of bits. You've got to take out the overflow. If you don't take out the overflow, then the whole system collapses. Because it is 4 bits, you've got to stick to the 4 bits. All right? Okay. So now our system is finally working. So when you have your calculator and it's doing some subtraction or division, it's using a 2's complement system. All right? Okay, let's look at another example. Let's do 25 minus 18. (25 minus 18) is the same as saying 25 plus negative 18. All right, and let's do this in 7 bits. All right. Tell me, do you think if I ask you to do it in 4 bits, would it work? What would be the problem if I asked you to attempt this problem in 4 bits? 4 bits. Yeah, it won't work because even one of the numbers, if one or both of the numbers, either one, if at least one of the numbers is greater than the 4 bits, so the largest number of 4 bits can entertain is what? 15. The largest number 4 bits can attain is 15. So anything greater than 15, 4 bits can't handle. So 6 bits would be able to handle it, but definitely not 4 bits. All right. So you've got to also note the number of bits being used. All right. Okay. So 25, guys. What do you have from 25? Let's flip back to your lecture notes. I gave you some homework in week 1. I said build a table. What do you get for 25 in natural binary? 11 001. 11 001. Is that natural binary? Okay, let's do this in 7 bits. So in 7 bits, that would be 1, 2, 2 padding, and then you have 11 001. Okay, 25. Let's look at 18. Let's look at positive 18. What do we get, guys? Positive 18 would be, we've taken the absolute value. I'm skipping that step because it's so simple. What do we get, guys? 1 1 0 0 1 0. Right? And in 7 bits, that would be 00 1 00 10. Okay. Now, negative 18. For negative 18, you take your positive 18, you have 00 1 00 10, you flip, that will become 1 11 0, then you add 1. One plus 1 is 1 0 1. Okay, and that's in 2's complement. That's in 2's complement. Okay, we all happy till there, right? So we now do 25 minus 18, 25 plus negative 18. The answer should come to 7, right? 25 minus 18 is 7. Okay? So 25 was what, guys? What was 25? I wrote that early on. That is 00 11 001, and we add 00 1 00 10. Let's add this up. 1 plus 0 is 1, 1 0 1 0, carry 1 1 0. Can we convert that number? Can we convert that number, guys? 1 plus 2, 1 2 4 8. Oh, sorry, I was supposed to use this one, eh? Okay. Okay. I used positive 18. I should have used negative 18. So it will be 00 11 001 plus this one here, the one right at the bottom of the page, 11 0 1 0. Okay, and this was, what was this? This was 25, this was minus 18. Yeah? Okay. So 1 plus 0 is 1, that's 1, 1, 0 carry 1, 0 carry 1, 0 carry 1, 0 carry 1. Right. So if we count the bits, 1, 2, 3, 4, 5, 6, 7, this is your overflow. Now what does 4 zeros 111 equal to? Well, 111 is equal to 7. So the answer is correct. Okay. All right. Now, there are some limitations. So we have our system over here. There are some limitations, and I've mentioned it early on. Remember, I asked you a trick question. I said, hey, how about if you do this in 4 bits? And he said, no, can't be done. Why it can't be done? Why cannot it be done? because, well, the number of bits cannot be occupied. Those numbers are too big to be occupying 4-bit systems. So there is a breaking point. It's not that 2's complement solves it all. 2's complement goes a long way. We were using sign magnitude. It gave absolutely the wrong answer. Really wrong answer. We used 1's complement. It gave the wrong answer, but the wrong answer was just short by 1. Just short by 1. So we corrected 1's complement. We enhanced 1's complement, and we ended up with 2's complement. So we are happy with 2's complement. But then, what we got to do? We've got to now apply 2's complement. We've got to look at the limitation, right, of 2's complement. So there are some limitations. Okay, let's now, before we look at the limitations, I want us to do the reverse of converting 2's complement to decimal. Let's go the other way around. We've gone decimal, negative number, to 2's complement, but what about the other way around? Okay, let's have a look at this number. We've been told that that's a 2's complement number. We've been told that that's a 2's complement number. Now, to start off with, we don't really know, so the rules for going from decimal, from a negative number to 2's complement was very straightforward. But going the other way around, there is some hiccups. What are the hiccups? Well, the hiccup is that, let's go and attempt whatever we did. Let's try and reverse process whatever we did early on, right? So we take 0, 0, 1, 0, 0, 1, 1, 0. We flip, so we're reversing the system. We flip, okay? We flip, and if we flip, we get 1, 0, 0, 1. Then we add 1, 0, carry 1, 1 over there. Now, there's some big questions. We've got this number here, right, 1010, which is equal to 10. Now, is this, we have to ask ourselves, is this a positive number or a negative number? Number of bits was not specified. Right? So we have some issues now. All right. So what we've got to do is we've got to now look at the reverse process, right, in a different manner, so that we achieve the right answer. All right, guys. We'll stop there for today. We have another lecture tomorrow, and we'll see you in the tutorials today. There will be a tutorial today, tutorial tomorrow, and tutorial Thursday. Right? Please make sure that you solve the tutorial sheet before you attend. Okay? Thank you, guys. All right?